Now let's talk about the estimation of difference between two binomial parameters, like the experimental group or control group. We also need a type of approach. So what do we mean by this? We're trying to estimate the difference between P1 and P2 populations. I mean, population 1 and population 2, their probabilities. So you need to do observation and sampling first. Observation and sampling from those populations. And you need to have N1 samples from the first population and N2 samples from the second population. And you will see X1 successes, like or what you're seeking as a binomial parameter, male or female, or heads or tails or whatever. Okay, this type of and X2 for the second population. So here your estimator is, which is an unbiased one, is the most straightforward one. The successes over the number of trials, one, and for the other population, that should be X2 over N2. All right, and so this one, this difference is the best estimator for, is the best estimator for what we're seeking for, what we're looking for, P1 minus P2, and this value right here will give you what we're looking for, P1 minus P2. And what about the variance of this difference? Variance of this P1 minus P2 is represented with sigma square, P1 minus, oh sorry, it's not very pretty, minus P2. All right, so it is P1 Q1 over N1 plus P2 Q2 over N2. That's it. And what about the error range for Chebyshev? Its error range is two standard errors, like as you can guess. Error range would be 2 square root of, oops, what is this? Square root of P1 Q1 over N1 plus P2 2 over N2. And if your N1 and N2 are large enough, I think you're getting used to this already. Like if we have more than 30 samples for each of them, it can be approximated to normal distribution. And for P1 minus P2, you can speak with the confidence level as well for 1 minus alpha confidence level. The corresponding confidence interval would be what? As you can guess, confidence interval, the corresponding confidence interval would be P1 minus P2 plus minus Z alpha over 2, and your standard error, right? P1 Q1 over N1 plus P2 Q2 over N2. That's it. So that's pretty. And let's try to implement what we have, or let's try to solve an example with what we have learned so far. Great. And this is the example from our textbook again. There are two insect killer chemicals, insect killer chemicals, namely, okay, mosquitoes, since the summer is approaching. Not approaching, it's already here, mosquitoes. We're trying to get rid of them, and there are two brands, okay? So in two different rooms, two identical rooms, we have N1 equals N2 equals 1,000 mosquitoes, okay? In two different identical rooms, we release 1,000 mosquitoes in each of them, and after the application of the first brand and the second brand in different rooms, in the first room we have 825 mosquitoes dead. Okay, we find them dead. And in room B, okay, or brand B, in the second room, we have 760 mosquitoes dead. So in this case, we're looking for this unknown population difference between those two brands. So this is required, but we don't have this, right? This is required. But what we have is their samples only. We don't know what is real, but we can estimate it, right? So this is your estimator. And what we have here is PA minus PB will result in what? This one over 1,000 minus this one, brand B, over 1,000, and the result will be this much of difference, okay? So this is what we have. Put this aside, okay? We have this one. And let's talk about the error range now. Error range. It's two standard deviations, right, for the Chebyshev theorem. But of course, we will talk about confidence interval in a few moments. So our error range would be what? Our error range would be 2 times our standard error on this one. This is your probability of killing it in the first room, and the probability of not killing it in the first room, over we have 1,000 mosquitoes, plus we have for the second room we have this one times 0.24. Okay, we don't need 0 for this, right? 0.24 multiple. Oh, wait, where there is a 1 here. Okay, now it's perfect. Pretty. Okay, pretty. Lovely. Okay, this is your error range for Chebyshev, and okay, this talks about any distribution, error range for any distribution, and at least 75% of sample X will fall within this range, plus and minus, right? But since we have lots of samples taken, like 1,000 from each one, which is much larger than 30 sample threshold, we can assume that it can be approximated to normal distribution, and we can also use our lovely normal distribution table as well for this purpose. And for PA minus PB, if we want to speak with 95% confidence, what do we have to do is we need to find the, don't rush, always draw this, okay? We need to decide on these bounds here. So this has to be, the shaded area has to be 0.5, which would be your alpha, right? So that should be your alpha. And what you will have here would be 0.25 and 0.25 right here. which is called, these are your Z alpha over 2, and this one would be minus Z alpha over 2. But since we cannot use the table directly, we can also find these important points here, these range here. What is this one? This is what we're looking for. And what is this area here? The remaining one, right? Okay, 0.475, right? So since it should be added to 0.5 here, so I need to find what this value is corresponding. Don't memorize anything. I beg you to, do this slowly and step by step, because there can be single-tailed calculations, so you don't need to rush anything here. Okay, what we're looking for has to be 0.4750. Okay, here is this one, and it is, as you see, 1.96. Lovely. It's 1.96. So I understand that those should be 1.96, this one, and this one should be minus 1.96. This is my range, and when I write this properly, PA minus PB plus minus 1.15. Okay, this is my coefficient for calculation, but I don't have space here. How can I write? So let me take this one. So let me take this one here, please. All right, because I don't have space. Okay, all right, and that should be my standard error right here, 0.25 times 0.175 over 1000 plus 0.76 times 0.24 over 1000. Lovely. Okay, I'm ready. So it is 0.65 plus minus 0.36. So I can conclude that my PA minus PB should be is between 0.29 to 0.101. All right. See, this is my lower bound, and this is my lower bound, and this is my upper bound. Okay, it should be something between. The difference is between. But I'm speaking with what? 95% confidence. Can it be different? Yes, but 95% confidence, all the trials should fall within this range. So as you see, when you correspond this to 0 in x-axis, you're left on the right-hand side here, like from 0.09 to 0.101 here. Since you are within this range, on the right-hand side of the, let's say, x-axis with respect to 0 here, you can say that, you can also conclude that brand A mosquito killer is more effective than brand B. You can also say this, right? Just pause the video and think about it. This is what's interesting about it. You can do this for something popular as well, like the vaccinations or something like this, comparing two brands. Okay, that's how they do it. That's how we compare two different, let's say, groups within this sense. But never forget, we're speaking with 95% confidence. We could choose 99% confidence here, but if maybe if we had chosen a confidence level this high, maybe this could be extended to this one, right? Then since it included 0, maybe we may not be easily saying that brand A is better than brand B, because then we could have 0 also placed within that range. That could be possible. I haven't calculated, but just building it up. Just to give you an idea about what about the confidence levels, okay? Anyway, that's the idea about the estimation of difference between two binomial parameters, and you can be sure that we will be talking more about this. We have methods for this, for testing hypotheses, which gives us very, very convenient tools for deciding such type of deciding the outcomes of such type of experiments. Okay, thank you for listening.